So, hi everybody. So yesterday I learned from my kids, amazing kids I have, that the octopuses are agile enough to be able to operate Rubik's cubes with their tentacles. Apparently they have like two very agile tentacles and they could really use them to turn the Rubik's cube around, but perhaps cannot yet actually solve it. So this is something I learned yesterday, and today I will try my best to teach you something about the superposition and the superposition principle. So as we know, the course is optics, and this is the table of contents for the course. And right now we're starting our lecture series on chapter 7 regarding the superposition. And here, this is essentially a prelude for the upcoming chapters where we will be treating interference effects and diffraction effects. So that will be the main motivation why you should learn and listen to these lectures I have regarding superposition. And what I will be speaking about in these upcoming 5 lectures, I will start by speaking about the superposition principle, and this I will do in a few minutes after this first motivation introduction to the chapters. And then what I will do in the next lecture, I will be speaking a little bit about the harmonic waves. So essentially we will try to generalize the notion of standing waves, not standing waves, but plane waves, so that we could really qualitatively understand propagation of fields. And we could understand propagation of fields inside different settings. So essentially, for example, different fibers inside different kind of waveguiding structures and even free space instruments. For example, interferometers, Mach-Zehnder interferometer and Michelson interferometer would be the main interferometers I'm thinking right now. So essentially, we're trying our best to generalize the concept of propagation of field, so the concept of a plane wave, so that we could really understand how more complicated instrumentation and scenarios actually work. And when we understand this propagation of light in these kind of structures, instruments, then we can generalize also how superposition of fields takes place in such instruments, and then we can basically calculate what kind of phase accumulation takes place. And once we know the phase accumulation, then we can calculate the superposition field and then consequent irradiation distribution. So essentially we can understand what kind of interference patterns arise in more complicated instrumentation. For example, when we make an interferometer, you're using 2 fibers or 2 waveguides, or in free space instrumentation. Then in chapter 7.3, so that will be our 3rd lecture on standing waves, I will consider superposition of 2 fields that form now a standing wave and not a propagating wave. And I will introduce to you the main terminology regarding standing waves. So that I will be discussing then. And then the lecture regarding superposition of several frequencies, I will again generalize things. So now I will generalize the concept of superposition. And here essentially I will be speaking about the Fourier theorem, the Fourier transforms of the field, and that as a useful piece of mathematics that can be understood, can be used to understand superposition of several frequencies. So there, essentially, I will connect the Fourier transformed field, so a field described in the frequency domain using the slang of Fourier transforms, with the spectrum of the actual physical field we're speaking here. So that's the kind of spectrum of the optical field of interest. And I will be showing a few example functions, and then I will be Fourier transforming them. So essentially performing some integrals and speaking a little bit about the uncertainty principle too, I think, in the end, which essentially arises from the properties of integral transforms, such as the Fourier transforms. So essentially when we have pairs of variables, so-called conjugate variables, then they are connected via different kinds of integral transformations, for example, the Fourier integrals in the x, y, z basis. And then it's really necessary that the uncertainty principle will be governing the interrelations of these 2 different conjugate variables. So for example, the frequency and time would be a preliminary example of these kind of conjugate variables. And then in final lecture regarding coherence, and I must warn you that the coherence is actually a very not the easiest of concepts in terms of optics and photonics and physics in general. So we can only be very introductory here and rudimentary. So this is really a difficult concept to grasp, and we cannot really go too deeply into coherence theory in our first beginning course in optics and photonics. So basically we would really need to develop a lot more math and understand and be able to use a lot more math to actually understand what is coherence. So we should actually take use of a stochastic treatment of the electrodynamic fields. So instead of just using a single plane waves, we should rather use a compilation of many planes with some kind of randomized phase distributions, and then we should be dealing with the math arising from these kind of complication. And we should also, in my opinion, better understand how light is being generated. So essentially, what kind of light-matter interactions there are. So essentially, getting back to our chapter 5 regarding light-matter interactions, so that we would understand how, for example, fluorescent molecules work, how light is being emitted when we excite fluorescent molecules, and how lasers work, and so forth, so that we would really understand where the coherence properties of propagating light arise. And where coherence properties of light really arises when we are thinking of propagation of light in a lossless medium, and that can be most of the time be considered to be a good approximation of the situation. Then it's really the coherence that is associated with generation of light. So essentially it boils down to understanding how the fluorescent molecules work and so forth, and what kind of laser conditions there are that are giving rise to the coherent laser emission and so forth. So basically, since we do not have the math and we really need to understand coherence, for example, we would really need to be more knowledgeable of using Fourier transforms, then we are really forced to a quite simplistic and conceptual treatment. So that will be what I will be using in my lecture regarding the coherence. So this is, in a nutshell, what I will be speaking about to you during these upcoming lectures regarding the chapter 7. And now I will start my first lecture regarding the superposition principle. So here in this chapter 7, essentially we will be understanding propagation of light as a motion of waves. And please remember, in chapter 10, we will be again going into the ray optics treatment. So we will be understanding how geometrical optics behaves and how we can understand propagation of light in that framework. And the motivation for this chapter is essentially to understand how we could understand and model phenomena and processes based on interference and diffraction. So this is basically a prelude chapter for these two upcoming chapters, 8 and 9, where we will be speaking in more detail about physics taking place when light interferes with light, and then what happens when we have diffraction effects. And these phenomena essentially they are based on the superposition principle and of the concept of superposition. So essentially, interference effects and diffraction effects, we are summing waves together, either like a discrete series of waves that gives me rise to interference effects, or we are summing up a continuous distribution of waves giving rise to diffraction effects. So basically, it's really the superposition principle and the concept of superposition that are the most important things to grasp here. And as always, when we are dealing with waves, we should start with something firm, giving us a firm grounding. So we start with the wave equation. So we take the Laplace of a psi, the wave, and we have a differential equation. So on the right hand side, we have the inverse of the velocity squared, so 1 over v squared. And then we take the second partial time derivative of the wave psi. So this is our familiar wave equation. And of course, this is now in a scalar form, but equally well, we could apply these to the vector wave. So we could really just replace e's here. And please, the same kind of equation would describe propagation of waves in a vector form. And these differential operations that we can see taking place inside in the equation, they are linear operations, so that essentially an arbitrary superposition of different kind of waves still acts as a wave. And what that means is that the superposition wave psi that I can write as a summation of all possible ways I can imagine, multiplied with some kind of coefficient to each of these sub-wavelets, psi i's, this superposition wave is also a solution of the wave equation. So this is what the superposition principle essentially means, and it arises from the fact that these differential operations are linear operators. Linear operations. So this gives rise to superposition principle, and this is super interesting and important in almost all branches of physics I can imagine. Like, this is a very strong assumption we always many times make in different branches of physics, and surprisingly many of the times this also applies, and this is a good approximation. And when that applies, we can really simplify our treatment quite a bit, because these different ways do not really interact with each other, but rather we can easily just sum different waves together, multiply them with the different kind of weights, and this weight also includes a possibility of having some kind of slightly different phases associated with the different subwaves, and then we can calculate the superposition field. So this is with what we start with in the upcoming lectures, so that now you know what you need to know in order to continue. So I will stop here. Thanks for listening my prelude for the chapter 7 on my first lecture regarding the superposition principle, which really is the key of understanding what follows. So I thank you, and please stay tuned.